Good morning students. I am Manpreet Kaur and today I will be teaching you about the introduction to classical mechanics. So first of all, what is classical mechanics? It is that branch of physics which deals with the study of motion of macroscopic particles. Now what are macroscopic particles? The particles which are visible to the naked eye, they are called as the macroscopic particles. Fine. So it's just a recall of the things which you already know. So first of all, as you all are aware, what is linear momentum? Linear momentum is a vector quantity and it is represented by P vector. And P vector is given as the product of mass with the velocity. Okay. So this linear momentum, it is basically deals with the translational motion. Next quantity which is of our interest is force. What is force? Force is basically a push or pull which is responsible for the motion of the body. So you all know that force is given as mass into acceleration, or from Newton's second law, force is given as rate of change of linear momentum. So F is either mass into acceleration or F is dP by dt. Now force is of two types. First force is conservative force and the other one is non-conservative force. What we mean by conservative forces, those forces for which the work done is independent of the path and depends only upon the initial and the final position, they are called as conservative forces. So basically for these forces, work done does not depend upon the path taken. For example, like gravitational forces, it only depends upon the initial and the final position. Then electrostatic forces and so on. On the other hand, what are non-conservative forces? Those forces for which work done depends upon the path taken and changes with the path, they are called as a non-conservative forces. For example, frictional forces or dissipative forces. So, non-conservative forces are those for which work done depends upon the path. Conservative forces are those for which work done is independent of the path and depends only upon the initial and the final position. Okay. For most of the time in the classical mechanics, we will be dealing with the conservative forces. So let's study more about them. Conservative forces are represented as force is equals to minus del of V. That is, these forces are represented as gradient of potential energy. Potential energy is a scalar, gradient is a vector quantity. So I can also write it as minus curly V upon curly R. So conservative forces are those forces which can be represented as minus curly V upon curly R or as del of V. Okay. Third quantity in which we are interested is the work done. So what is work basically? Work is defined as the dot product of force and displacement. So work done will be, suppose if dr is the small displacement, then the work done, small work done for this displacement will be F dot dr, okay, where F can be conservative force or it can be non-conservative forces. So fourth quantity in which we are interested is kinetic energy. Kinetic energy is represented with capital T and it is defined as 1 by 2 mv square. It is the energy which is possessed by the body by virtue of its motion. So whenever a body is moving, it is having some kinetic energy and that kinetic energy depends upon the mass of the body as well as of the velocity of the body. Fifth quantity in which we are interested, it is potential energy. we represent potential energy with the symbol V? It is defined as that energy which is possessed by the body by virtue of its position. Okay, for example, you know the gravitational potential energy. It is given as mgh, where m is the mass of the body, g is the acceleration due to gravity, and h is the height of the body from the ground. So similarly, potential energy is nothing but it is the energy possessed by the body by virtue of its position, and it is defined as the amount of work done to bring a unit mass from infinity to the given point. Okay, so if I am talking about gravitational potential energy, it will be simply mgh, or in general potential energy will be equals to integral negative sign f dot dr. From where I have taken this relation? I have taken this relation from here. Here I have stated force is equals to derivative of potential energy. So potential energy can be represented as integral of force with respect to the displacement. So potential energy is f dot dr integral with the negative sign. Okay. As far as all these quantities are concerned, they are limited to the translational motion. What is translational motion? Translational motion means when a particle is moving in 1, 2 or 3 dimensional along a curve. Okay, so all these quantities, they are limited to the translational motion. But what will happen when the body starts rotating? So for that case, we have to take a quantity which will be similar to the linear momentum, a quantity which will be similar to the force. So now let's talk about the rotational motion quantities. So as linear momentum defines the motion of the particle in translational motion, similarly we have angular momentum which defines the motion of the particle in the rotational motion. So next quantity, sixth, is your angular momentum. Angular momentum is represented by alphabet capital L, and it is given as L is equals to cross product of R, where R is a position vector, with the P, where P is a linear momentum. So basically what is angular momentum? It is the moment of momentum, or in simple words we can say the momentum in the rotational motion is angular momentum L. Okay. Then next quantity is torque. Torque is N. It is analogous to the force in the translational motion. Okay. So what is torque? Torque is defined as the moment of the force R cross F. Okay, and as you know that we have written, if you remember, we have written F is equals to dP by dt, right? So similarly we can write torque is equals to rate of change of angular momentum, that is N will be equals to dl upon dt. That is, torque is rate of change of angular momentum. So my main concern is that if I am talking about translational motion, okay, so as in translational motion we have force is equals to rate of change of linear momentum. Similarly in the rotational motion we will have torque is equals to rate of change of angular momentum. Okay. Now the last thing which you must know is the Newton's laws of motion. If you remember, Newton has given 3 laws of motion, and Newton is also considered as a father of classical mechanics. That is why sometimes we also refer classical mechanics as Newtonian mechanics. So what are the 3 laws of Newton's? Newton's first law, it states that a body will remain in its state of rest or in uniform motion until or unless it is disturbed by some external force. Fine. Newton's second law, it states that force is directly proportional to rate of change of linear momentum. This thing. Okay. And This law also gives us force as mass into acceleration if mass is taken as constant. Okay. What is third law? Third law states that to every action there is an equal and opposite reaction. For example, if there are two bodies, 1 and 2, and the force which first body exerts on the second is given as F21, then F21 will be equals to minus of F12. This means force on 2 due to 1 is same in magnitude as force on 1 due to 2, but the direction will be opposite. So this negative sign shows opposite direction. Equality sign shows that their magnitudes are same. That is okay. So you must take here a pause of 5 minutes by yourself and recall all these things in your mind before starting with the actual article of classical mechanics. So we will be starting with the first article, which deals with the motion of a single particle. Okay, now let's start with the first article of the topic, that is mechanics of a single particle. So a single particle means I have a one particle which has mass m and it is moving with the velocity v. It can be moving in one dimension, it can be moving in two dimension, it can be moving in three dimension. I consider a three-dimensional frame of reference in which my particle is moving, say, along x-axis. Okay. So what is the linear momentum of this particle? Linear momentum will be P is equals to mass into velocity. Okay. And from Newton's second law, we know that force is equals to rate of change of linear momentum. Okay, call this equation as equation number 1, where F is the applied force, or you can say F is the external source. Now what will happen if this force ceases to exist? Means what will happen if this force vanishes? So at F is equals to 0, I will have dP by dt is equals to 0. Now we all know that if time derivative of a quantity is 0, that means that quantity is a constant of motion. Very good. So P will be constant of motion. Or in other words, I can say when force vanishes, then linear momentum is conserved. So first is conservation of linear momentum. It states that if external force vanishes, then linear momentum is constant. I hope this is clear to you. So basically in the mechanics, we'll be dealing with the three conservation laws. First conservation law is conservation of linear momentum. Second conservation law will be conservation of angular momentum. And third conservation will be conservation of energy. So first of all, when there is no external force, then linear momentum will be constant or it will be conserved. Fine. Now next is conservation of angular momentum. Second is conservation of angular momentum. So if you all remember, earlier we have discussed that angular momentum is nothing but the moment of momentum. So consider a particle in a three-dimensional frame, 0, x, y, z. Suppose this is my particle of mass m, which is at the position vector r from the origin. And this particle is moving along this curve, say. So momentum or velocity will be along this direction. And L is given as cross product of position vector with the linear momentum vector. We all know that direction of L will be perpendicular to the plane which has both R as well as P. So L will be in the direction R cross P perpendicular. Okay. So taking derivative with respect to time on both sides. So what will happen is, when I take derivative on both sides, I will have dl upon dt. This will be equals to d by dt of r cross p. Okay. So I use the formula as first function as it is into derivative of the second plus derivative of the first cross second function as it is. Okay. So I can write it as r cross dp by dt plus dr upon dt. What is it? It is basically velocity, as it is rate of change of displacement. So this becomes v cross, momentum is what? Mass into velocity. Okay. So this becomes dp by dt is nothing but force. Mass being the scalar quantity will come out, and I will have cross product of velocity with the velocity. We know that when two same vectors are cross multiplied, we get 0, because if you remember, what is A cross A? It is nothing but magnitude of A into magnitude of A into sine of angle between them. So angle between them is 0, which means this will be 0. So what I get is, I get dl upon dt. This is nothing but r cross f. So if you remember, what was r cross f? R cross f was nothing but torque. So what will I get? I will get dl upon dt. This is equals to torque n. So what will happen when torque vanishes? When torque will be 0, this implies dl upon dt. This is 0, which makes L is equals to constant. So this is my conservation of angular momentum, which states that when torque is 0, then angular momentum is constant. So first, which talks about the translational motion, we have linear momentum as constant. When we talk about rotational motion, we say that when torque vanishes, external torque vanishes, then angular momentum of the system is a constant of motion. Last but not the least is conservation of energy. So third is conservation of energy. There are many types of energies in the system, like heat energy, like sound energy, but we are interested only in two types of energies. First one is the kinetic energy and second one is the potential energy. and together they are called as mechanical energy. So what is mechanical energy? It is nothing but sum of potential energy and kinetic energy. So when I say conservation of energy, I mean that mechanical energy should be conserved. Okay. So first of all, energy will be conserved if and only if forces are conservative. Means forces, they are derivable from the potential energy. If forces are non-conservative, then energy will not be conserved, because some energy will always be dissipated either in the form of sound or in the form of heat. Okay. So whenever we want energy to be conserved, our first requirement is that the forces we are dealing with should be conservative in nature. So first is this thing. Now consider a small displacement dr. When this force is applied on the system. Now when force is applied and there is some displacement, we will have some work done and that work done will be dot product of force with the displacement. So dW should be F dot dr. Substituting the value of force. What is force? Minus curly V upon curly R dot dr. As there is only one variable, position, that is r, so instead of writing the partial derivatives, that is curly, I can simply write it as minus dv upon dr dot dr. Okay. Now there is derivative with respect to dr and dot product with respect to dr, and this is a small work done for a small displacement dr. The total work done in displacing the particle from point 1 to point 2 will be simply integral of dW from 1 to 2, or work done from 1 to 2 will be equals to minus integral 1 to 2 Now integral is with respect to position vector r, derivative is with respect to position vector r. They both will cancel out and I will be left with my function only v, which is to be evaluated at 1 and 2. So what will this give me? Minus potential energy at 2 minus potential energy at point 1, or V1 minus V2. This is my work done. Okay, this is my work done in terms of potential energy. But if I want the conservation of energy, I need both potential as well as kinetic energy. So half part is done. I am having the equation of potential energy. Now half part is left where I need kinetic energy. So how to take kinetic energy? Again we will take work done dW. This work done will be equals to force into displacement dr. Okay. Now we know that what is force? Force is nothing but mass into acceleration. Okay. What is acceleration? Acceleration is nothing but rate of change of velocity. So I am having mass into dv by dt dot dr. This is my work done. Now I am having two variables here. One variable is r, the other variable is v. I will try to take two variables or change two variables into one. So we know that what is velocity? It is nothing but rate of change of displacement. So I can write dr, this will be v into dt. This dt I have taken to the other side. Okay. Now substituting this value of dr in this equation. So we will have dw, this will be equals to m dv by dt dot v into dt. This equation can be written as dw as d by dt of 1 by 2 mv square into dt. We can check how I have written this equation. So dv dot v upon dt, square can always be written as a dot product. So what will this become? 1 by 2m first function as it is into derivative of the second plus derivative of the first into second function as it is. So these two terms, they are same. So this becomes 1 by 2m 2 times v dot dv by dt. 2 and 2 got cancelled. I will be left with m, which is my same expression, m dv by dt dot v. So whenever I have one derivative dot product with the function, I can always write it as d by dt of 1 by 2 mv square. And what is 1 by 2 mv square? It is nothing but kinetic energy. Okay. So total work done from position 1 to 2 will be integral of this work done from 1 to 2, or W12, this will be integral from 1 to 2. Again same thing, derivative with respect to time as well as integral with respect to time. They both will cancel and I will be left with the function only. Or W12, this will be T2 minus T1. Call this equation as equation 2. Now, if I compare this relation with my first equation, I will have, from the first equation we have written W12, this was V1 minus V2. So from 1 and 2, their left hand sides are same, which means their right hand sides would be same. So V1 minus V2, this should be T2 minus T1, or V1 plus T1, this is T2 plus V2, or E1 is equals to E2. This means mechanical energy remains conserved. As total energy at point 1 or initial point is same as the total energy at point 2, that is final point. So let's have a recap what we have done today. We have firstly introduced the quantities which you are already aware of, like linear momentum, force, angular momentum, torque, work done, kinetic energy, potential energy, and Newton's laws. Okay. Then we studied the mechanics of a particle. What we have done, if external force vanishes, then linear momentum is constant. If external torque vanishes, then angular momentum is constant. And third, if forces are conservative, then mechanical energy is conserved. Okay, that's all for now. Stay healthy, stay safe at home. Thank you very much.